Hi, I'm Unipro, and today I'm going to teach you about the importance of nuclear fission, the importance it has in our everyday lives, and the importance it could also have in the future. Say I took a half-inch metal pellet, about this big, right? And I told you it could produce as much energy as 149 gallons of oil. It may seem crazy, but a half-inch pellet of uranium-235 is what is in our reactors and produces as much energy as 149 gallons of oil. Back in 1945, if you told somebody that one day their homes would be powered with half-inch metal pellets, they'd call you crazy. But nowadays, 10% of world homes are powered with nuclear energy. To understand where nuclear energy comes from, it's important to understand two things. First of all, nuclear fission, and second of all, radioactivity. So first off, radioactivity. Radioactivity is the instability of an atom's nucleus due to an imbalance between the strong forces binding the nucleons and the Coulomb forces repulsing each proton, making the atom emit a particle to balance out these forces. Second off is fission. When an unstable atom, such as uranium, is hit by a neutron, it then splits into two and emits 3 neutrons. These facts, coupled with Einstein's famous equation relating mass and energy of an object, is the key to understanding the origin of nuclear energy. E is the possible energy contained in the mass, in joules, m is the mass of the object in kilograms, and c is the speed of light, in meters per second. So let's work with the reaction between uranium-235 and a neutron. We see that when uranium-235 is hit by a neutron, it splits, as we know, into 2 other atoms and releases 3 other neutrons that in turn go to hit more neutrons and then they hit other things. So it's a chain reaction. But where does nuclear energy come from in this reaction? Well, let's look at the mass of the reactants and the mass of the products. By the law of conservation of mass, there should be an equal mass of reactants and products. However, by adding up the sum of the reactants and the sum of the products, we see that there is a little bit less products than reactants. And Einstein tells us with his famous equation that this mass deficiency, the mass of the reactants minus the mass of the products right here, is actually transformed into energy, into pure energy according to his equation E equals m times c squared. So here we have a few nuclear reactions that we can use to apply what we just learned and calculate how much energy they each give off. So let's just work with the first reaction right here, see if we can figure out how much energy it gives off. We've got one neutron with one nitrogen that gives off a carbon and a proton. We're going to be working with the equation that we learned about, E equals m reactants, the mass of the reactants minus the mass of the products, times the speed of light squared. We find in the book the mass of the proton that we need, the mass of the neutron, and we also look at the table, periodic table, we find the molar mass of nitrogen and the molar mass of carbon. Now we can't take these directly because we need the mass of a single atom of nitrogen and a single atom of carbon. So we need to divide these molar masses, the molar mass of nitrogen, by Avogadro's number to get the mass of a single atom of nitrogen. So we're going to have, with the equation, using the equation above, E equals m reactants, so mass of a single atom of nitrogen plus the mass of a neutron minus the mass of an atom of carbon, so that's the molar mass of carbon divided by Avogadro's number, plus, between parentheses, the mass of a proton times the speed of light squared. And that's going to give us the energy that this reaction gives off. So the goal right here is to figure out which reaction has the most energy, releases the most energy, and we basically just repeat those steps for the other 2 reactions. I already calculated the different energies these would get off, and it seems that the third reaction right here is the reaction that gives off the most energy. So molybdenum and a hydrogen nucleus giving off technetium and a neutron is the nuclear reaction that releases the most energy. So here we've got a slightly more interesting problem because it actually applies in the real world in actual nuclear reactors. So we've got a typical nuclear reactor that uses uranium-235 as the fuel, which fissions according to this reaction. Knowing that an American home uses this many joules per year, we have to calculate the amount of reactions needed to happen in that reactor to power the home. So what we're going to be doing right here is calculating the energy that this reaction gives off in joules using the equation that we saw before, where E equals the mass of the reactants minus the mass of the products times the speed of light squared. And we know that the mass of the reactants right here is the mass of uranium-235 plus the mass of a neutron minus the mass of the products, which is the mass of barium-141 plus the mass of krypton-92 plus the mass of 3 neutrons, so 3 mass of neutron, times the speed of light squared. So this is what I calculated right here. A single reaction releases, with the equation right here, the mass of uranium plus the mass of a neutron minus the mass of barium-141 minus mass of krypton-92 minus 3 mass of neutrons times the speed of light squared, which gives us that a single reaction releases 7.92 times 10 to the minus 10 joules. We know that the house uses this many joules a year, so we divide that value by the amount of energy produced by a single reaction to know how many reactions we need to power a home during that year.